Okay, so I'm just going to review some of the things that you saw in Module 10. So one of the lead-ins to Module 10 was this idea that model diagnostics are not as available for logistic regression as with linear regression, and for the following reasons, right? The various goodness of fit tests do not work with ungrouped data, and most of the time what you will see will be ungrouped data. Unless you have a well-designed experiment. In that case, you could have grouped data. We also explored plotting the log odds versus the predictor. Well, that only works with one predictor and maybe two if you're able to produce a three-dimensional plot. But you can't do this in high dimensions. And examining a plot of residuals doesn't really help us due to the discrete nature of the response variable in logistic regression. So what we'll do is basically just evaluate the performance of the logistic regression in terms of how well it does in predicting outcomes. And so we kind of say, right, usually what we do, right, is we have a decision rule or a threshold to decide how we classify predictions. So for example, if your estimated probability is greater than half, maybe you classify that observation as a success, otherwise it's a quote-unquote failure, right? This value of 0.5 is called a threshold. And we say that, well, we could also create a confusion matrix, right, to see how many false positives and how many false negatives we have. And the values do depend on the cutoff value, right? As you vary the cutoff value, the values of the error, the proportion of errors, false positive rates, false negative rates will change. Generally speaking, so in a binary setting, a cutoff of 0.5 gives the highest accuracy rate on average. So this is on average. It's not a guarantee. Right, so for specific data sets and specific splits of the training and test data, this may not be the case, but on average, this will be the case. Depending on the context, you actually may be more interested in ensuring high sensitivity or high specificity, right, i.e. low false negative and low or low false positive rates rather than the accuracy. So if that's the case, then you will have to vary the cutoff value accordingly, right, or the threshold. So I kind of interchanged cutoff value and threshold over here, so I apologize for that. ROC curve, right, plots the true positive rate or the sensitivity against the false positive rate, 1 minus the specificity for varying cutoff values or threshold. And we kind of say, right, if the logistic regression does no better than random guessing, i.e. it doesn't use info provided by the predictors, then the true positive rate is equal to the false positive rate, right? Because if you're going to randomly guess k% of observations to be positive, then among all true positives, k% of them will be classified as positive, right? So this probability over here, which is the sensitivity, is just k%. And if you randomly guess k% of observations, right, to be positive, then among all true negatives, k% of them will be classified as positive, and this is the false positive rate. So basically, we are saying that, right, the true positive rate and the false positive rate will be equal to each other, and so therefore the ROC curve along the diagonal indicates a model that does no better than random guessing. A few words of caution, right? I kind of mentioned this. Accuracy can be misleading, especially when you have unbalanced sample sizes of the two classes. So just be very careful with that, right? Don't just evaluate the accuracy without looking at the confusion matrix and or calculating the false positive and false negative rates. Our C curve shows the true positive and false positive rates as the threshold is varied. It does not immediately inform you of the true positive and false positive rates for your specific threshold, right? So you have no idea, right, on that curve, which part of that curve refers to your specific threshold. And likewise, right, the AUC is a summary, right, of the performance for all possible values of the threshold. It doesn't inform you anything about the accuracy for your specific threshold. Right, so that's logistic regression validation. We kind of then moved on to multinomial logistic regression, which allows us to have a response variable that has more than two classes. The key idea here, right, is it's always important to note in your response variable which class is going to be the reference class, because what happens, right, is that you're modeling the log relative risk as a linear combination of your coefficients and predictors, and the log relative risk compares the probability of belonging to class C versus the probability of belonging to the reference class. So what you have will be separate equations for the relative risk for each class versus the reference class, right? So if you have m plus 1 classes, there will be m of these equations, or m logits. Each logit models the log relative risk of belonging to a specific class versus the reference class, right, as a linear combination. So for each logit, right, the values of these betas, estimated values of betas will be different, right, because you're doing different comparisons. Last but not least, we kind of had a little bit of reading on generalized linear models, and I will just make some general comments of these. So generalized linear models are a family of regression models, so they are like a bigger umbrella group of regression models, right, of which we've seen the logistic regression. Their coefficients are estimated using the method of maximum likelihood. All right, so far we've seen linear regression and logistic regression. We have estimated linear regression using ordinary least squares, not with method of maximum likelihood. Now, it turns out the linear regression model can also be estimated via the method of maximum likelihood. And both methods converge asymptotically. So if you have a large enough sample size, both methods should result in values that converge with each other. Now, one thing I'll mention is that the method of maximum likelihood for linear regression is much more sensitive to the assumption of normality of the error terms, right? Whereas for ordinary least squares, I kind of say it's not super sensitive to that assumption. So logistic regression is a specific kind of generalized linear model. Another common one that you might use is what we call a Poisson regression, which is used to model count data. So your response variable is a non-negative integer, right? Because count data basically you're counting the number of times something happens, right? So count data will be integers, right? 0, 1, 2, 3. It cannot be negative. It could include 0. And for any generalized linear model, we can use the following test, right? You can use the wall test to see if you can drop a single term. You can use the difference in the non-residual deviances to test if a model is useful, and you can use the difference in the residual deviances to compare nested models, right? We did that in logistic regression. All these things can be also done for any generalized linear model that was fitted with method of maximum likelihood.